So now on to the papers. There's been a lot of papers that have come out the past couple of months, and fortunately, I can't cover all of them, but I've chosen a selection of the papers that I found interesting. The first one I'm going to talk about is one that I'm co-author on, and it's by Rovere et al., and it was published in the May 1st, 2025 issue of Geomorphology, and the title is Reconstructing Past Sea Level Changes from Storm-Built Beach Ridges. So this paper is, the data is derived from the fieldwork that I did in 2019, which was led by Alessio Rovere, and this particular paper focuses on a site near the town of Coleto, Libya, and this is located sort of in central Argentina along the Atlantic coast. And this was actually the first site that we visited when we were doing our field trip or our field work. So anyway, what is the purpose of this paper? So along the coast of Argentina, there are these beach ridges that are preserved all along the coastline. And these beach ridges, some of them represent fossil beach ridges that formed in past interglacials, so periods when sea level was higher than present. And in Coleto, Libya, there's a fossil beach ridge that is above 10 meters higher than the present-day sea level. And the purpose of this paper is to create a definition of how to define what sea level was for a beach ridge. So what is a beach ridge, of course? Basically, in a beach, you'll see a ridge along the coastline that's above the high tide mark, and this ridge is basically formed during storm waves. So when there's a storm, the waves are higher, so it pushes material higher than the high tide level. And in places like in Patagonia and Argentina, these beach ridges are very prominent, and they're full of rocks, and it's obvious that there's a lot of energy that's required to create these beach ridges. So the first thing that Alessio did in this paper is he defined the paleo sea level based on an analog from the present-day beach. So we measured with a GPS the elevation of different features of the beach and found basically where the interface between the high tide level and where the beach ridge sort of forms, like where the storm waves are depositing the material. And based on comparing the same kind of feature on the fossil beach ridge, he found that the paleo sea level was 14.5 plus or minus 2 meters higher than the present day. And just as a note, this fossil beach ridge, the exact age is not really well constrained, but it either dates to the last interglacial or the second last interglacial. So somewhere between 200 and 110,000 years ago or so. The second component of this paper is because we have a really good modern day data, as well as a nice section which we can precisely define the fossil beach ridge compared to the modern beach ridge. We wanted to use that information to come up with a way to define what the paleo sea level when we don't have a modern beach ridge to use as a comparison, or when we don't have a complete section of the fossil beach ridge. So Alessio created a methodology using satellite data. So he took satellite data from satellite altimetry measurements of the wave height in the ocean close to the site, and used that to calculate the statistics of the average height of waves in this part of Patagonia. And so that was the first thing that he did. And the second component was to come up with a measurement of the slope of the shore platform. So basically, along the coastline, you measure the elevation along the coastline to see how steep it is. And that basically is required because it can tell you how high the waves can get along that part of the coastline. And that was determined using Landsat and Sentinel data. And basically using that information and calculating how high the storm waves would be based on that the wave height data and the slope of the coastline. Alessio's calculation showed that there's a pretty close correspondence to where the beach ridge forms on the modern beach. And therefore, you can use that information to create a modern analog in places where you don't necessarily have a modern beach ridge to go off of. And the accuracy, and basically using that technique and the modern analog technique and some other techniques that had been used in the past, there's pretty close correspondence to calculating the paleo sea level at the Caleta Olivia site, which is great. That's great. That's what you want to see. And it has narrowed the uncertainty on the paleo sea level. And yeah, obviously I'm pretty happy about that because I wrote a paper a few years ago on the determining the past sea level from these beach ridges, and we didn't have this kind of information, and the uncertainty on the paleo sea level estimates was quite high. So yeah, anyway, moving on. Yeah, there's been so many great papers in the past 2 months, and I'm going to highlight a few of them just very briefly. So the first one I'm going to highlight is by Barker et al., and this paper was published in the February 28th issue of Science, and the title is Distinct Rules for Precession, Obliquity, and Eccentricity in Pleistocene 100,000-year cycles. And so in the last episode, I talked about how orbital variability is the primary control of climate change on 1,000 to 100,000 year cycles. And what Barker et al. Wanted to prove is that there was a strong link between the changes in the Earth's axis of rotation and the timing of deglaciation and the start of glaciation on either side of an interglacial period. And what they found is that using the oxygen isotope records from the ocean, if you align sort of the center point of the deglacial period with the peak in precession forcing for the northern hemisphere summer insolation, using that as sort of the tie point. In every single case, the next glacial cycle starts when the obliquity is decreasing, so that basically the obliquity forcing is decreasing in the northern hemisphere summer, and this rule seems to apply to every single glacial cycle in the past 800,000 years. And so basically it creates a rule about when deglaciation happens and when glaciation starts again in an orbital sense. And they also used it to predict when the next glacial cycle would start in the absence of anthropogenic carbon dioxide. And they said it would probably be within the next 10,000 years or so. The next paper was by Creel et al., and this was published in December in Nature Communications, and the title is Global Mean Sea Level Was Higher Than Present During the Holocene. And basically what they were looking at is trying to determine what the global average sea level was in the past 10,000 years, and using a whole bunch of different ice sheet reconstructions and Earth model structures. They calculated hundreds of thousands of different sea level reconstructions for the world, and then they compared that against a fairly large data set of relative sea level data from around the world, and based on rejecting various results based on their misfit from what the data said compared to what the modeled sea level was, they were able to deduce that between about 7,500 years ago and 3,200 years ago, global average sea level was probably higher than present. And yeah, so that's good to pin down, because basically prior estimates were saying that sea level remained below present day level for most of the Holocene, but that really didn't make sense, because we also know that the Greenland ice sheet and parts of the Antarctic ice sheets were smaller than present during the Holocene. So yeah, that's a really nice study by Roger Creel. Of course, I would be remiss if I didn't talk about sea level compilations, and the first I'm going to talk about is by DeWitt et al., and this was published in the February issue of Earth System Science Data, and the title is HolCNL, a Holocene water level and sea level indicator data set for the Netherlands. And what I have to say about this, there have been compilations of paleo sea level data in the Netherlands, and it was already a really well constrained sea level history for the past 8,000 years or so. But this really takes it up another notch, and I'd say it's probably the best constrained paleo sea level history in a regional sense anywhere in the world. And they tightly constrain the sea level history in the Netherlands for the past 9,000 years. And what's interesting about the Netherlands is that over the past few thousand years, sea level has been slowly rising in the Netherlands, and this is a result of glacial isostatic adjustment processes. So in Scandinavia, the land is rising, and because of that, the land in the Netherlands is dropping. So there's still this rebound from the ice loading in the last glaciation in Scandinavia, and basically the material deep below the surface is moving back towards Scandinavia, and that is why sea level is dropping or sea level is rising in the Netherlands. And there's another compilation, and it's by Vacchi et al., and it was published in Nature Communications in February, and it was titled Sea Level Since Last Glacial Maximum from the Atlantic Coast of Africa. And so this was the first compilation of paleo sea level data on the western side of Africa, and this place is a great place to look at paleo sea level, because there's not a whole lot of impacts from tectonics, so we don't have to worry about vertical land motions due to tectonic activity. At least not a whole lot there. It's kind of similar to Patagonia in some ways, but it's a little bit different because the continental shelf is not so wide. And basically, what I found interesting is that it brought to light some data from the last glacial maximum, so between 20 and 25,000 years ago, that I previously didn't know about. And I think most scientists looking at modeling past sea level also didn't know about it. And these data are from around Cameroon, and it suggests that in that area, sea level was between about 100 and 110 meters lower than present during the last glacial maximum. And this is a bit higher than estimates in some other parts of the world, and that's likely a result of its proximity to the northern hemisphere ice sheet. So, we talk about in this glacial isostatic adjustment world that there's the so-called eustatic sea level or global average sea level, but there's not really a lot of places that you would consider to be at this sort of average level, because the signal of glacial isostatic adjustment is a global signal. So yeah, this paper, I'll be excited to put it into my own database so that I can use it in my own analysis. Anyway, this is probably a long podcast, so yeah, hopefully it won't take 2 months until the next one, and because there's always lots of great studies coming out, and I do want to highlight what I find to be most interesting. So anyway, have a happy March. Bye-bye.